Hello everyone, welcome to my channel, and we have three circuits here. We have this, that is a relay flip-flop, the alternating blinking of the LED with the use of a relay. And this is my previous project. We have also this. This is a transistor flip-flop using transistor to produce an alternating LED flasher. And the other one, that one, is being controlled by our Arduino using the Arduino programs here. LED flip-flop, and that is the program I use to control the blinking, alternate blinking of the LED. So we have the PLC controlled or microcontroller controlled. We have the transistor controlled and then relay control. What is the drawback of my design? Well, the drawback is it seems my control is fixed, but this is reusable. You can use it anytime using the program. But this one, my control system is fixed. I need to design a control system or a switchboard that I can be able to reuse it while building a project. So let us see my new module. This is a switchboard module capable of controlling the blinking of the LED, and you can use the one side, the other side, or both, and also capable of controlling the external output or outboard, aside from having this an onboard LED flasher that serve as a monitor if the external output is running. So we have this. We have here some jumper settings for onboard operation and also for controlling the external output. So this is a switchboard. What is the use of this module? As a switch. Also, this is a oscillator circuit, just like the other three. They are all oscillator circuit. This is also known as Transistor Astable Multivibrator. But we can reuse this by controlling the external output, and we have the input LED monitor or indicator. By changing the jumper settings of this module, we can control the blinking of the LED. We're going to use the one side, the other side. So let us now see the circuit. I have two power provision here. I've got 5 volts and 9 volts. So I'm going to use this 5 volts. And then the 9 volts, then the ground, there's still no lights. So I'm going to patch the use the jumper for 5 volts. So the control system is now powering on. Did you see the light? Let us now see our input. Okay, change that to red. 5 volts control power supply, and then let us now see our input LED, a flashing LED at the right side, and then patch the other one, the jumper settings. So we got now this, an alternating LED flasher. So we have this, an input control system. How about the output? Can we see the output by using this LED output? Let us check the output. Still, there's no light. We can make that put to light by making a jumper. Did you see that? The right output LED responds to the right input controlled LED. And let us now patch the other output. Still, we don't get that again. And this is now our output using 5 volts. It seems it's a little dimmer. The lights are getting dimmer. What if we're going to use a 9 volts? Let us change the jumper settings into 9 volts. So we get this, a very bright light. So every time the input LED turns on, it means the output is turning on also. What is the use of this module? This is a control module. It can provide an oscillator circuit or a clock or controlling any kind of circuit by using if you're going to use just 1/2 of the output. There you go. Or the other half. Let us see there. The other half. So we have now this, an oscillator circuit. It is capable of providing a clock pulse to the circuit, at the same time function as a switch that making the circuit to turn on and off. Unlike that previous one, this is also a transistor and is a stable mode operation, but it is fixed. The circuit is limited. The application of the circuit is limited only for this project, while this one This is reusable. We can use this as an oscillator circuit to any circuit and as a clock that provide this oscillation, the alternating, blinking, flashing of the LED. We can use 9 volts or 5 volts by changing the jumper settings. We can use one LED or one output of this multivibrator by changing this jumper settings, either left or right. So this is a it has multiple uses or usage. I can reuse this in any project I'm going to build. So let us now see the design of my control system. If you are interested with this, why is it that this type of LED flashing there is some sort of a delay? We can see that in our diagram. The diagram of this alternate flashing of LED is just this, a transistor flip-flop. This is in a stable mode operation. The LED is connected through between the resistor and to the capacitor that produces an alternating flashing by the action of charging and discharging of the capacitor. With 9 volts, the values of the resistor is practical, arbitrary values. I just this is the practical values of the resistor, 10K to the base. They are coupled, the input to the output, the feedback system of the circuit. I'm using this 222A transistor, BJT NPN. 1K to the series with the LED, 100 microfarad. That is the diagram of this one. That's why it has different blinking pattern, because the LED is connected this way. Why this one? We're going to see the circuit diagram. And we have this. The circuit diagram is this. Where is that? This one. See the relay? The ticking sound of the relay. This is now our new circuit. First, this is the initial circuit. I got 9 volts and there's no values of the capacitor and the resistors in the circuit. We're going to compute for the values. That is the regular astable mode of the transistor multivibrator. We have the Q1, transistor 1, 2N3904, Q2, 2N3904, connected via capacitor, the output of the Q1 connected to the input of the Q2. Collector resistor, base resistor, capacitors, coupling capacitor, resistor. We have the output. Did you see the difference with this one and this one? The output now is taken into the collector emitter of the transistor. Just like unlike the previous one, it is connected in series with the resistor. Now it's different. Also I have this power on LED. we need this power on LED, that is the green one, for power indicator. Once you power on the circuit, this LED turns on. So what is this? A stable multivibrator application. It has no stable state. So there's no stable state for the circuit because it keeps on changing the state from 0 to 1. It oscillates. It produces a rectangular or square wave. I think it's a square wave because of the behavior of the LED. It turns on and off continuously. And the uses, this is a switchboard control to any circuit. So I'm going to design, I designed this for control, as a control system, or as a clock control system for the circuit. So we got this in the data sheet of the diode and also the transistor. It is all given: HFV, CESAT, VE, current rating of the LED, and the voltage rating. We're going to find the values of all the resistors. So let us now begin. Solution. Use figure 2. So we have now here figure 2, circuit on, node analysis. When you power on the circuit, current flows into this node, also this node, this, here, and here. Let us first see the first KVL into the power LED on once you turn on the circuit. So we got here, when you circuit on, due to the doping properties of the transistor, the tolerance of the resistor and capacitor raising occurs. That is the characteristic of this circuit. There is a raising, the occurrence of the raising due to the doping properties of the transistor, the tolerance of the transistor. In theory, once you power on the circuit, it will both operate, or the Q1 should be in saturation at the same time. In this one is saturation, but because of the doping properties, it will not happen that way. That our electronics devices and components are purely imperfect. It shows. So during the raising, of course, so either one of these two, well, first to turn on, either this one or this one. So let us say Q1 on and Q2 off. Power LED turns on. So let us say this one is the one first to turn on due to the raising. We get to solve for the values of RD3 by taking the KVL. BCC, RD3, D3. We get 7 volts, 9 volts. Using Ohm's law, we know the voltage rating, current rating. This one is 2, this one is ampere. So we got 330 ohms, my available resistor. That is the available resistor in the market. So we got now the value of resistor here using KVL. We got also have a KVL here, BCC to RC2 D2. BCC RC2 D2. Since the initial condition, current flows in this way. It means capacitor in this way is charging, making the current to flow into the capacitor, making the transistor to forward bias, and also the current flows into the LED because this is cut off due to the negative potential by this capacitor. Because once you power on the circuit, current flows here to the LED, charging the capacitor. Also, there is a current flows here, providing a continuous power supply, and also current flows into the capacitor. This is now discharging. Once this is discharging, this is in saturation. Once this is in charging, this is discharging. We have this, a resistor. Let us now compute see the voltage drop across RC2. This way, BCC, RC2, B2, KBL. This is now on. Power LED, the output on, the Q1 is on. That is our initial condition. We get now voltage drop of 7 volts across BRC2. 9 volts voltage rating of LED. Using Ohm's law, we know that already. Voltage at RC2, current, we got 330 ohms across RC2. Now, C2 is charging. Forward biasing the Q1. So, in this KBL, current also in this node, current flows into this node, into the right. We know that already, the KBL. Also, current flows here into the capacitor, charging the capacitor. What happens is when it is fully charged, it will make the circuit to open this portion when the capacitor is fully charged. What happens is this current now is now going to provide a continuous current flow from this RB1. So this one now is open. It cannot produce a continuous current flow. Supply of current. Once this is fully charged, because at this state, this capacitor is charging. Once it is fully charged, this is equivalent to open circuit. And what happened is the current flows into the base, forward biasing the transistor through RB1. So we got now here ICQ due to the potential at -1. Full charge is now open. Okay, ICQ. So because why is it that there's no current flows here? Because no triggering current here. Because that time this state, this one now is, remember this is charging, the capacitor is charging here. This one is discharging, discharges to this RB2 to C1, dumping to CE to the ground. Also current flows into the RC1. That is the characteristic of the initial state of the circuit. So we're going to use the KBL across BCC to QBE SAT, RB1. KBL, RB1 to QBE SAT. So there's a current KBL, complete circuit here. BCC, voltage up RB1, and the forward biasing of the transistor. We got a voltage drop here of 0.7 in the case of silicon transistor. BE SAT. We got now here the BE SAT voltage drop at RC1 8.05. Why is it so? RB1, the RB1. Forward biasing the transistor. When there's a triggering current here, makes transistor to saturate. There is current flows also here from collector to base of the emitter. Because this is in discharging mode, making this a negative potential to the base of this transistor. That way this is cut off at this state. Okay, let us now see another figure here. Okay. We now know the value of the two resistors, the RC2 and RD3. Now we have the Q1 on, Q2 off. Still, KBL at BCC, BRC1, the output side of the transistor 1. So there's also KBL here because this is saturated, making the output to turn off. Because the transistor is served as a switch, it will cause this to turn off. Current flows directly to the ground. BCC minus voltage drop RC1, collector emitter at saturation. Where is that? This. We get a voltage drop RC1, 8.7. Okay. Now, what else? Okay, now at the time that it changes the state, because due to the racing state or the racing condition, we get now this transistor Q2 now is on, Q1 now is off. It means there is an output on here and the output at the other side is off, because now this is saturated or current close to the ground. This is the alternate state. When Q1 is on, the Q2 is on, Q1 is off, Q1 is off, Q2 on. Using BCC to compute for RC1, BCC to D1, RC1 to D1. So where is that? Okay, this one. So we get now the output of the other LED to turn on because there's a current close here to the ground. Computing for the values of RC1 there is just the KBL, BD1, RC1. We get 7 volts using Ohm's law. We got 330, what is that? RC1 here. 330 ohms, the value of the resistor, now RC1. Due to this state, this is saturated, this is off. Due to the negative potential again, capacitor, current flows into the LED and charging through here. So now we got now here KBL at BCC, RB2, QB is at. So making this to forward bias the other side, the other capacitor, the charging, due to the charging. Just like as I've said, this is when it is fully charged, it will equivalent to open circuit. What happened is there's a continuous supply of current through RB1, making this transistor to operate in forward bias. We can calculate the RB1, voltage drop at RB1 by using the KBL, BCC, RB1 minus the voltage emitter saturation, voltage drop, the Q2. We got 8.05 volts voltage at RB2. Now in this type of configuration, the transistor is dependent on the current gain. We get a current gain formula for Q2. ICQ2 is also equal to a current at IRC2. So the current here is also ICQ2 and also equal to the current at the D2. Using that formula, collector over the base, we get now this. Since I'm using current gain HFP of 100 by transposition calculation, I got current at the base is IRB2 0.0002 ampere. Knowing the current at RIB2 using Ohm's law, we know the voltage drop at RB2 with this formula KBL is, and the current by the current gain, we got now 40 kilo ohms. That is now the value of RB2. Okay, now it toggles again. So it toggles again. Once it toggles again, we can now compute for the Q1 the same formula, 0.002. Since this stable circuit, same 40 kilo ohms. The RB1, RB2 is equal to 40 kilo ohms. RC1 is equal to RC2. Since the circuit is symmetric, and we got this, that is now the charging effect of the capacitor, the discharging, 0.6069, while I'm using this one, 40,000, 30,000. What is the value of capacitor to be used to provide 1 second of pulsating? I think this is 36.2 times negative 6 microfarad. I'm using 47 microfarad to produce this time constant of 1 second. The pulse duration of the circuit, I'm using 47 microfarad. The pulse duration is 1 second. The sum of the two on and off pulse duration of the LED. 1 second. 1001 on and off. And now you can now use this schematic diagram for making this circuit diagram for making the transistor astable multivibrator. RB1 330 ohms, RB2 40K, 40K, RC2 330, 330, power on LED, output 2, Q2, Q1, 2N3904. That is the circuit diagram. Coupling capacitor 47 microfarad, 16 volts. I'm using also this. These are my, well, this is my header. These are my layouts. Changing the jumper settings. Making this to operate in just one LED flasher, to operate one LED flasher by using the change in jumper settings, the in and out of the current, the reverse, the return, complete, the power supply header, jumper settings for the output 1, jumper settings output 2, sa jumper settings for the output using external, for the power using 5 volts or 9 volts. This one is the jumper settings for onboard LED and for external output. And then we got this output header for the other output. I'm using this full layout. So that's the operation of our switchboard module control that is capable of producing a clock pulse. It is an oscillator circuit. We can use this in many applications. We can reuse this, recycle to any circuits we're going to build in the future. Okay, thank you for watching. Bye bye.